Welcome back to the video series. Let's recap Secure Solutions' original problem they are trying to solve for. They launched a new subscription service for their camera devices, and they want to accomplish a couple of things. They want a unified users table that has all the helpful attributes needed to better inform their marketing efforts so that they can create more targeted audiences specific to the user journey. Within these distinct audiences, they will have tailored, personalized messages. This will allow them to create more efficient campaigns with higher conversion rates. They also want to enable push notifications based on camera activity to their users who opt in. But that can only happen if they know what devices belong to what users. The majority of this video series has dealt with the underlying problem that blocks these use cases, the ID resolution problem. Now that we have built a healthy ID graph, we can now use that in order to compute accurate features for our users. The remaining videos will cover how to build these features, how to unify them within one final feature view within the warehouse, and finally, how to schedule this project to run in production. In this video, we will cover how to build specific features and output them to a single view where each user is represented in one row along with their computed features. For this video series, we will not define all of the features that may be needed for Secure Solutions use cases, but we will define a handful in order to see the structure and how they work, as well as the flexibility with which they can be defined. Let's go back into our Profiles YAML file. We will define a new root key called var groups. Nested underneath this key is where you will define groups of features that you want to compute. This is different than defining individual features. The purpose of defining the groups first is to create a localized dictionary of features that would be specific to a group. The flexibility of defining groups allows you to create dedicated features for more than one entity if you have more than one, or to create dedicated features for defined cohorts of a specific entity. For the purpose of this series, we will simply define one group for our user's entity. In this group, we will define the specific user features. Let's define a group name using the name key. Within this named group, we will link the entity that the subsequently defined features will belong to using the entity key users. The YAML key used to define a feature is called an entity var. Let's create our first couple of entity variables. For our feature view, we want to have the first and last name of the user. Let's define those here. We will now review the structure and formatting of an entity var. Each entity var will have a name. This represents the column that will generate within your final view. Next, we have the description. This is an optional key used to define a more human-readable definition on what each column or feature is. We then define an abstracted query structure that we will use to generate the feature. You will notice the formatting is very similar to a common SQL statement that you would write directly against the source tables to compute features. We have select, from, where, and window keys you can use, where you will provide the SQL needed to extract the data from the target columns from your inputs. Any SQL that is valid within your data warehouse will be valid here. A quick note on how these features compute the derived values and why the generation of the main ID via the ID graph was necessary in the first place. You will notice as we build out these entity vars that we always use either an aggregate function or a window function within the select statements. These are required in order for the templated SQL that gets generated to work. Let's think back to what we are trying to do in the first place. We are not simply selecting columns from our source tables. We are computing features across the tables for our users, which means we need to group and partition our data appropriately. If we were to access a single event source table and compute a first seen column, we would most likely run the following query. This would give us the first time we have seen this user within this specific source. But the chances of a user having a single anonymous ID are very small. Also, we have many sources we need to consider in order to get a true first seen date. Instead of grouping or partitioning the data by the anonymous ID, we need a higher level key. This is where the ID graph comes into play. Underneath the hood, we are joining the ID graph back to your source tables so that we can then use the resolved main ID as the column to group and partition the data. Profiles groups and partitions the data automatically within the entity var definitions, leading to an accurately derived value. Now, Back to defining the entity vars. Let's walk through this first feature. We will name it account first name and give it description. Next, we will define the select statement. We know that we can get the user's first and last name from our orders table since they have to input their name within the order checkout process. Given that a user could have completed multiple orders, we will need to use a window function here to select the first name value within their partition. We will then define the source table in the from key. Notice we are not pasting in the data warehouse table directly. Instead, we are referencing our input definition for that table. The full table name will then be resolved in the compile step of a run. Given that we are using a window function, we then want to define the partition window. We will order by the timestamp column in descending order. We will then do the same thing for the last name entity var, simply changing the column we want to target. Next, we want to define a feature that represents the total number of devices that a user has ordered. See the var definition here. In this feature, we defined a count function within the select and then define the source table to perform this count on. Again, profiles will group by the user main ID automatically. In the next feature, we will introduce a new concept. That is, using a custom SQL model as a source as opposed to a raw input source. We want to define a feature that accurately counts the number of sessions a user has had on our marketing website. We know that we have a number of event tables, so computing a feature from a single source would not give us the accurate value. For this feature, we will have to perform a union across our different event tables within the marketing website schema. This can be accomplished within your current profiles project by using a new model type we have yet to use, the SQL template model. Let's create a new YAML file. We will name it SQL models, and we will define this model definition within this file. A quick note about custom SQL models. Sometimes your source tables may not be in the desired format for feature computation. Custom SQL models provide the flexibility to write custom SQL transformations that may be needed for either ID resolution or feature computation. Within the model definition, you can choose to run the SQL ephemerally or output it as a materialized table or view. In this case, we want to define a feature which counts the total number of sessions a user has had on our marketing website. But a single input source will not suffice. We need to create a new source for this feature to perform the count on. Here's our model definition we need for this feature. We will give this model a name, which we can then reference later. We only need this SQL to run ephemerally, so we will define that in the output type. Beneath that, you can see the SQL used for the model definition. We are selecting all the common fields needed across some of the event tables from our marketing site. Notice that we are defining the raw inputs in the Jinja code above the SQL. This is so that profiles can correctly construct the dependency graph from the raw sources. I did not define all the inputs here, just a couple to illustrate the point. In this case, we are referencing the previously defined inputs within the inputs YAML file. This model will be used for feature computation. This means that it will also need a join with the ID graph. So we also want to define the columns within this model that represent identifiers just like we did for our input definitions. This will allow profiles to join the ID graph to this SQL model so that it can use the main ID to group the data appropriately. Now, let's define our feature that uses this model as its input. Notice the difference in the from clause here. We are no longer referencing a raw input definition. We are now referencing the model name that we defined within our SQL model's YAML file. Next, Secure Solutions wants to have a user feature which contains device details for all the devices a user has bought. Let's define a feature that is an array of JSON objects that contain the device details for each device a user owns. You can see here how we can define much more complex features using SQL functions native to Snowflake. I will also define a timestamp feature, which represents the last date a user updated their cart. I will call this max timestamp cart update. Lastly, let's introduce one more concept. There may be cases where you would want to derive a new feature value based on a previously calculated feature. You're able to accomplish this within profiles as well. We want to calculate the number of days that have passed since a user has updated their cart. In order to do this, we will have to reference the values of our feature, above called max timestamp cart update. A few things to notice about the syntax difference in this entity var. Notice the syntax used to reference another entity var. Also notice that we are not performing an aggregate or window function within this entity var. The reason here is that the underlying table we are referencing in order to perform this function is a base table that Profiles builds for your entity. The grain of this table is one record per main ID. There's no need to group or partition the data in this case. We are simply selecting a column from this base table and performing a calculation against it. In this case, we are performing a date difference function in order to derive the number of days since each user has added something to their cart. I will now paste in the rest of the entity vars that Secure Solutions needs. We now have a handful of features defined. As mentioned above, when defining features, Profiles is constructing a base table called the entity var table. This table is not meant to be activated. Rather, it is used as a target table to output all of the computed features. This table is then used as one of the base tables for the final view that is meant to be activated. This final view is called the feature view. In the next video, we will define a feature view and query the output.